Hello, my students. This is a brief walkthrough through the van der Waals equation. The van der Waals equation makes adjustments to the ideal gas law to have it apply to real gases. So I guess we could call the van der Waals equation the real gas law. If we remember, the kinetic molecular theory gives a perfect description of an ideal gas, saying that gases are composed of mainly empty space, that the distance between the particles is so great that we can ignore the volume the particles have themselves. So the particles, gas particles, have no volume. We also say that a gas moves in rapid random motion, that when gas particles collide, they are elastic collisions. There is no net loss of energy. We also say that the temperature of the gas is directly proportional to the kinetic energy, and that the particles themselves do not exert attraction on each other. Well, these are the two main violations that really make a real gas a real gas. So, when we take a look at real gases, like nitrogen, like helium, like carbon dioxide. Now, if we have 1 mole of gas, and we take pressure times volume divided by R times temperature. Well, if we have 1 mole of a gas, the pressure, volume, and temperature always yield the value of 1 for PV equals nRT. However, if we measure real gases, they vary from that nice vertical alignment, mainly because of these two things. So, what makes a real gas is the particles do have volume and the particles do attract each other. So, Johann van der Waals adjusted the ideal gas law. He came up with what we call the van der Waals equation. The van der Waals equation. Now, if we see, we've made an adjustment to pressure and an adjustment to volume, but it still equals nRT. So how do these account for real gas behavior? Why don't we look at this one? The gas particles themselves do have volume. When we insert into PV equals nRT the volume of our gas, we are really just accounting for the volume of the container. We are saying the volume of the container equals the volume of the gas. But that isn't true. That is ignoring the actual volume of the particles themselves. What van der Waals did was added this correction to account for the particle volume. N, remember, is moles, and B is a constant depending upon your gas. So, if we take moles times the value of B, what it does is corrects for us, subtracting away the role of the actual gas particle volume, so that volume will truly be the volume of the gas, not the volume of the container, disregarding the volume of the actual particles. So we're really looking at the volume then outside of the actual particle volume. That would be the true gas volume. Now, what about pressure? We know that gas particles do attract each other. They do. This pressure is really a result of the collisions of gas particles with themselves and the walls of the container. And we are saying that that pressure that we would measure indirectly with the udiometer or with some kind of pressure gauge is the pressure of the gas. However, gas particles attract. So they actually hold each other back from the forcefulness of the collisions that would be exerted if they really did not attract each other. When a gas particle is moving to collide with the walls of the container, if there's another gas particle that it travels by, it's slowed down by that. That actually takes away from the forcefulness that it would use to hit the walls of the container or encounter another particle, or affect the piston within a gas pressure gauge. So what we do to account for the sluggishness, if you will, that the particles cause on each other because of their attraction, we're going to add this correction value. Now the correction value is a result of the number of moles as well as the volume in which the gas is existing times this A value, which, just like B, is dependent upon the material. Now if we take a look at the values of A, they pretty much increase as we go from top to bottom. But if we look at these guys, these are our noble gases. We know they are monoatomic and they are nonpolar. Well, why does the value of A go up as we go down the list of our noble gases? Well, as we go down, we know that London dispersion forces increase with number of electrons and molecular weight. So thereby, the attraction increases. So the effect of one xenon on another xenon is greater than the effect of one helium versus another helium as far as the effect on the pressure. So we need to show that xenon really should be hitting the walls of the container or the pressure gauge much more forcefully. It's a bigger molecule, it'll have greater attraction. Well, then if we look at water, polar, nonpolar, nonpolar, polar, but we of course have a really nice arrangement for hydrogen bonding with water as well as ammonia, but this will show a greater efficiency. So it makes sense this is a greater A value than this. Carbon dioxide is nonpolar, although it's larger than these nonpolar guys. So we're going to see a greater A value for them and so on. So it's good to know what, of course, the van der Waals equation is, why we make these adjustments. Usually what we are doing with this equation is solving for what the true pressure would be, or the true volume. And so I have an example here with my work shown for nitrogen. So what we're being asked, if you have 0.5 of a mole of nitrogen and you're given the volume and the temperature, use the ideal gas law to find the pressure, which would be 3.873 atm. Then use the van der Waals equation, and being very careful just to make sure that we're plugging in the correct variables where they need to be. What we actually find is the pressure using the van der Waals equation is greater than the pressure using the ideal gas law, which we would expect because a real gas will have a greater true pressure because the attraction of the particles are slowing themselves down. So the pressure according to the ideal gas law is of a lower value. So this is really the true pressure that this sample of gas would be showing. You can be expected to be given the A and the B values and be asked to solve using the van der Waals equation for either pressure or volume. You are not being asked to memorize the van der Waals equation, you will be provided it. Best of luck, and forward me any of your questions.